Hi there and welcome to this video for Senior Physics on Nuclear Physics. In this video we're going to be exploring half-life. Now we know that basically when we get an unstable nucleus it is going to spit out the various particles and it may transmutate into another type of element. Okay, so we may get fission where the nucleus splits into two and the result is, or 2, 3, 4, and it will split up into various elements and particles will be coming out. So half-life, as we know, basically is the time taken for half the number of atoms to decrease. So it's the time that is required. So if you've got a half-life of 5,000 years, it's going to take 5,000 years for half the number of atoms to decay down or transmute into their subsequent elements. So although we can't say yes, it's definitely going to happen, we can predict what's likely to happen via the various equations. So let's look at this equation we've got here. We've got nitrogen 13 is going to break down into carbon 12, liberating a positron. Okay, now if we had 10,000 nitrogen 13 atoms, what we would expect to see is around 12 of them would decay within 1 second. Now this is just an arbitrary number, but basically what that would mean is that we've got a disintegration rate or a decay rate of 12 atoms every second. So hopefully that makes sense. So the activity is 12 s to the negative 2. So we're losing 12 atoms every single second. So after 1 second, we get 9,988 atoms which are left over. After the next second, 12 more atoms would actually decay, and we get 9,976, and so forth and so on. Now, what's happening is, as the number of atoms decreases, so does the decay rate of the sample. Now, after 10 minutes, if we carried on this process, what we would find is we'd have 5,000 nitrogen 13 atoms left. And this is half the number that we started with, remembering we were starting at 10,000. So what we would then say is the decay rate at this point would be 6 disintegrations per second. So basically we've gone from our 10,000 all the way through to our 5,000 atoms. After another 10 minutes has elapsed, we'd have 2,500 atoms, which is half of the point where we'd started. Okay, not where we started, but after that 10 minutes. So we go from 10,000 to 5,000 in 10 minutes, and then from 5,000 to 2,500 in 10 minutes. And if we went to half, 2,500, we'd then it would take a further 10 minutes. The rate would actually decrease by half though, because of the number of atoms that we've got left over. So the period of 10 minutes is what's known as the half-life, because it's the time taken for half the number of atoms to actually decay. Now, the time taken for decay can often be written as just in seconds, and the SI unit for this now is becquerels, where 1 becquerel is 1 disintegration per second, or 1 dps, or 1 s to the negative 1. So obviously if you've got less active substances, the activity can be expressed in minutes, or we could go even further and look at years, depending on how long it's going to take for those atoms to break down. Now obviously this half-life can be put onto a graph. So if we know the time it takes for those disintegrations to occur, we can then plot that onto a graph. Now you can see, if I just go back, you can see in the table there, we've got time elapsed in minutes, we've got numbers of N13 atoms remaining, and then we've got the decay rate on the right hand side. So we've gone from 12 to 6 to 3 to 1.5 to 0.75. And what we get is this inverse curve, which has been generated. Now this inverse curve is basically our half-life curve. And you can see that when we look at the curve, we've got 10 minutes, is where we've dropped from 10,000 to 500 atoms. 20 minutes is the halfway point where we've dropped from 5,000 to 2,500 minutes. And then as we carry on, the next 10 minutes will be half of that, the next 10 minutes will be half of that, the next 10 minutes will be half of that, and so on and so forth. So the decay rate has basically produced this inverse curve, or half-life. Now the half-life time is always going to be the same. We're always going to get the same time for you to drop by half. So as a result, we can then utilize this to find out what the number of atoms are, and we can plot it back to work back on the idea of, well, what is how long ago has this been decaying for, if we were able to work out what those numbers happen to be. So we'll also notice that we're going to get different samples are going to be giving off a different decay rate all the time, and the half-life is going to vary. So lead, if you can look at this table here, lead you can see has a half-life which is infinite. What does that mean? It doesn't break down at all. Its nucleus is totally stable. Uranium breaks down 4.51 billion years is its half-life. So uranium-234 is going to take 4.51 billion years for it to break down to half the number. As we go on, you can see that TH34 has got 24.1 days, RN222 has got 2.82 days. They are taking a very small amount of time. PO218 is 3.05 minutes. You see PO214, the isotope, is 1.64 times 10 to the negative 4 seconds. So it breaks down rapidly, really, really quickly. And finally, we've got a proton there, takes 10 to the 37 years in order to break down. It's a phenomenal amount of time. Again, very, very stable. Now, so we've got this idea that different particles will decay at different rates, and as a result, they will have shallower or steeper curves as a result of that. Your job is to basically to be able to interpret the graph, produce the graph, or work out what's the time or what is the number of atoms that are going to be left over or starting with. And we can use an algorithm to say it to help us with this, which has come from the graph. Now the algorithm that we use is n equals n0 brackets half to the n, where n0 is the original number of atoms, n is the atoms at any given time, and subscript n is the number of half-lives which are generated. Now if you look at other videos in the course, they will run through similar equations. Some have been changed accordingly, but all you need to know is that this is what we use at St. Hilda's. However, if you go to any of the textbooks or onto the web, there are other equations that can be utilized. They are from the same equation. So don't get confused with a different equation here to what you might be taught in your school. There are two equations which are available. So let's run through an example which will allow us to explain how this works. So we've got a sample of iodine-131, has a half-life of 8 days and undergoes beta decay according to the equation below. I-131 goes to xenon-131, and we are going to emit an electron. Now it says if a milk sample contains 3 times 10 to the 18 atoms at a particular time, we've got to calculate the number of atoms remaining after 60 days, excuse me, and the time that would have elapsed after there have been 1 million atoms left. Okay, so let's look at the first thing. Now, if you want to pause the video and have a go yourself, then go for it. Otherwise, we'll go through it now. So I'll give you a second to pause it. All right, I will carry on. So let's have a look at the solution. Well, the number of half-lives elapsed. Now, we don't know that for A. We know that we've got 80 days. We know the half-life is 8 days. Sorry, we've got number remaining after 60 days. So we've got 60 days, and we know the half-life is eight days. So how many half-lives is 60 days is what we're going to ask ourselves. So by dividing 60 by 8, that will tell us the number of half-lives. We know that we start with 3 times 10 to the 18 atoms. So we know that n is going to be 3 times 10 to the 18. So as a result, we can substitute that into the equation, and we end up with n coming through at 1.6 times 10 to the 16. So our equation was 3 times 10 to the 18 times half to the power of 7.5. And that gives us the number of atoms. So the next question then asks is, what is the time to elapse for there to be 1 million atoms left over? So I start with 3 times 10 to the 18. I finish with 1 million atoms, so which is 1 times 10 to the 6. So n is going to be 1 times 10 to the 6, and 0 is going to be 3 times 10 to the 18. I need to find what subscript n is, and here's the solution. So you can see there we've put down our formula. N equals n0 times half to the n. So we've substituted in the values there. 1 times 10 to the 6 equals 3 times 10 to the 18. So that's what I want to finish with and what I started with, and I've got half to the n. So I've got to find out what that subscript is. So I've taken the number of starting atoms to the other side. So I get 3.333 times 10 to the negative 13 equals a half to the n. Then what I'm going to do is find the natural log of both sides, and what that will do is pull the n value down. So when we find the natural log of both sides, I get negative 12 to the 48 equals n times negative 0.301. Then all I've got to do is to divide by two values together. That will give me the number of half-lives. Now I know what the half-life is 8 days. So as a result, by multiplying that number of half-lives by 8 will give me the total number of days that that it takes to produce that 1 million number of atoms. Okay, so I hope you found that useful. The equations are going to be fairly similar depending on what type of equation you happen to use. So as a result, we can produce the graph. If we produce the graph, we could then find the half-life from what we're starting with, because it's going to work out basically from half the values. So you could be given a whole load of data, given the graph, draw the graph, then you find the half-life. Once you've got your half-life, you can then use these algorithms to work out the number of atoms or the amount of time that it's going to take for you to go from one place to the other. Okay, now I have put another example down video which you can run through, and there are also some really good videos. Khan Academy has done some really good work on putting together different forms of the equation. They use a different one to us, but basically it's the same process. So whichever equation you've been taught, run through those and utilize them. But both videos hopefully should be able to give you an idea as to what's happening in both situations. Okay, well I hope you found that useful, and thank you for joining me, and I look forward to seeing you again. Bye for now.